As you drift into sleep, imagine our galaxy, a calm ocean of stars called the Milky Way. Tonight we'll travel through 100 peaceful facts that reveal its quiet beauty. If you enjoy this cosmic escape, please like, subscribe and share, and tell us in the comments what part of the night sky brings you the most peace. Thank you for watching now. Close your eyes and let's begin. The Milky Way belongs to a much larger structure known as the Laniakea supercluster, a region so vast that light takes hundreds of millions of years to cross it. Within this supercluster, thousands of galaxies drift together through the same gravitational basin, drawn by faint currents of cosmic attraction. The Milky Way lies on one of the filaments connecting larger groups like a single island among many within an immense cosmic archipelago. Around this part of the universe, the density of galaxies is gentle, not crowded, and their motions are measured in hundreds of kilometers per second, yet across such distance the effect appears slow and smooth. Astronomers define Laniakea not by clear borders, but by the shared flow of galaxies toward a central region known as the Great Attractor, a concentration of mass hidden behind our own galactic plane. The Milky Way, together with its companions, moves gradually along this current part of a quiet drift that has continued for billions of years. This movement is not through space in the ordinary sense, but a graceful response to gravity shaping space-time itself. The volume of Laniakea contains the local group the Virgo cluster and many smaller threads of galaxies. Though enormous, it remains only one portion of an even larger cosmic web, where each filament of light and matter connects to others across unimaginable distances. Seen from far away, the supercluster would resemble a faint network of shimmering lines, each marking clusters of galaxies suspended in near emptiness. The Milky Way's location in this structure is modest, neither at the edge nor at the core, yet perfectly placed within a gently curving flow that defines our cosmic address. The environment around it is calm. The nearest massive clusters are tens of millions of light-years away, and collisions between galaxies here are rare compared with denser regions of the universe. Observations made by telescopes tracking the motions of thousands of galaxies have shown that Laniakea spans roughly 520 million light-years across and contains more than 100,000 galaxies. Each one, including our own, contributes to the collective pull that defines this domain. The term Laniakea means immense heaven in Hawaiian, a name chosen to reflect both its scale and its serenity. The Milky Way's trajectory within it is toward the same focal region, as many neighbours, a quiet migration that will take countless billions of years to complete. Despite this slow drift, the distances between galaxies within Laniakea are so great that the sky from any one of them would still appear mostly empty, scattered only with faint points of light marking the others. Gravity binds these galaxies loosely, not in a single clump, but through a delicate web of influences extending over unimaginable scales. The space between them is filled with thin gas heated to millions of degrees, so rarefied that even a cubic meter would contain only a few atoms. This medium glows faintly in X-ray light, invisible to human eyes, forming a background of soft radiation through which galaxies glide. The Milky Way's motion relative to this background can be measured from the slight shift in temperature of the cosmic microwave background, a sign that our galaxy is indeed moving as part of this large structure. The study of Laniakea helps astronomers understand that galaxies are not isolated but interconnected through gravity and dark matter. These filaments of mass formed early in cosmic history as matter condensed from the uniform plasma of the young universe. Over billions of years, gravity amplified tiny irregularities leading to the grand patterns visible today. The Milky Way's existence within one of these filaments reveals that even a single galaxy's story begins far beyond itself. The surroundings are tranquil, not shaped by recent collisions or violent bursts. The last major merger influencing our galaxy occurred long ago, and since then the Milky Way has moved through space largely undisturbed. The supercluster environment allows it to rotate peacefully, maintaining its spiral structure without interference from larger neighbours. The gravitational tides from other clusters within Laniakea are subtle, influencing the general flow, but not the internal dynamics of the Milky Way. At these scales, distances are expressed not in kilometres, but in millions of light years, and the light we observe from the nearest clusters left them before complex life existed on Earth. Still, by mapping the motion of galaxies and comparing their velocities, astronomers can trace the outline of Laniakea like the pattern of waves on a cosmic ocean. The Milky Way and its companions drift toward the Great Attractor region at about 600 kilometers per second, yet in the immensity of space this motion feels almost motionless, a steady glide through calm cosmic waters. In every direction around the Milky Way lie galaxies of many forms, spirals, ellipticals, irregulars, all contributing to the balanced structure of the supercluster. Some are bright and massive like Andromeda. Others are small dim systems containing only a few million stars. Together they form the luminous threads of the cosmic web, a pattern repeated across the observable universe. The Laniakea supercluster reminds us that the Milky Way is not the centre of anything, but one participant in a vast slow dance of matter. Within this region, gravitational interactions evolve over timescales far beyond human comprehension, where a single orbit around a cluster might take tens of billions of years. Despite the scale, the structure remains coherent, showing that gravity's influence extends seamlessly from the scale of planets to that of superclusters. Each galaxy carries with it a history of stars, gas and dust that originated long before the supercluster itself took shape. The Milky Way's gentle position within Laniakea provides a stable setting for its continued evolution, allowing its spiral arms to persist for billions of years more. All motion here is relative, all change gradual, and every light we see across the deep field represents another participant in the same vast flow. The stillness of the night sky, when viewed from Earth, conceals this movement, yet the evidence lies in the subtle drift of galaxies measured through careful observation. Thus begins the quiet journey inward from the largest scales of the universe toward the heart of our own galaxy, each step smaller, each layer denser, but all connected by gravity's continuous silent thread. Within the quiet immensity of Laniakea, the Milky Way resides inside a smaller gravitationally bound family known as the Local Group. This cluster of roughly 50 galaxies spans about 10 million light-year across and drifts together through the supercluster's larger flow. The Local Group's centre of mass lies somewhere between the Milky Way and the Andromeda Galaxy, two great spirals locked in a slow, mutual orbit that will take billions of years to close. The entire system moves as a single island through the cosmic ocean, following gentle gravitational tides set by still greater structures. The Milky Way and Andromeda are the two largest members of this group together, containing the majority of its stellar mass. Around them drift many smaller companions, each one a galaxy of its own, though most are far fainter than the naked eye could ever see. Between these systems stretches vast intergalactic space filled with thin gas and dark matter, nearly empty, yet quietly shaping their collective motion. Observations show that the Milky Way and Andromeda approach one another at about 110 kilometers per second, a motion so gradual that their eventual meeting lies roughly 4 billion years ahead. When they do merge, the result will be a single large elliptical galaxy, sometimes called Milky Way, though that event belongs to a future beyond imagination. For now they remain separate spirals, each rotating calmly in its own domain. The Triangulum galaxy, smaller but still significant, completes the trio of major members and orbits not far from Andromeda. It acts as a faint bridge in this three-body system, adding subtle complexity to the gravitational interplay that binds the local group. Around these three central galaxies orbit dozens of dwarfs, many containing only a few million stars. Some are irregular in shape, faint clouds barely distinguishable from the background. Others, like the large and small Magellanic clouds, are more pronounced and visible, even to the unaided human eye from the southern hemisphere. These two companions are among the nearest external galaxies, their soft glow part of the Milky Way's southern sky. The local group is defined not by proximity alone, but by shared gravitational coherence. All of its members, from the largest spirals to the smallest spheroidal dwarfs, remain bound together in a slow shared motion through space. Beyond its outer limit, other groups begin the Sculptor group, the Maffei group, each drifting within the greater network of the Laniakea supercluster. The distances between galaxies in the local group are immense, yet small enough that light from one can still reach another within millions of years rather than billions. Astronomers have traced thin streams of stars between systems remnants of past interactions, where gravity pulled material from one to another. These stellar bridges show that the galaxies are not isolated, but connected through ancient encounters, their faint trails crossing the empty dark between them. The mass of the entire local group, including dark matter, may exceed 3 trillion times that of the Sun. Most of this mass lies not in stars but in invisible dark halos surrounding each galaxy, extending far beyond their visible edges. These halos act like cocoons of gravity, keeping the system bound even across vast separations. Within this stable framework, galaxies move like leaves floating in a vast slow whirlpool, each following its own trajectory yet never escaping the group's overall pull. The temperature of intergalactic gas here is low compared with denser clusters. Radiation flows gently, and few energetic events disturb the calm. Even supernovae, when they occur within these galaxies, are too distant from one another to affect the group's shared environment. Each system shines with its own light, separated by millions of light years, yet part of the same gravitational story. The local group's boundaries are subtle, fading into the surrounding cosmic web without clear edges. Astronomers identify them by the balance between internal gravity and external expansion beyond a certain radius. Galaxies drift away with the general expansion of the universe rather than remain tied to the group. This boundary, called the zero-velocity surface, marks the quiet limit, where cosmic expansion overtakes local attraction. Within it, the Milky Way and its companions remain stable, rotating gently around their common center of mass. The Andromeda galaxy itself is slightly larger than the Milky Way, spanning more than 200,000 light-years. Its disk is tilted at an angle, and through telescopes its spiral arms appear filled with blue star clusters and lanes of dark dust. In contrast, the Milky Way's structure must be inferred from inside through mapping and observation, since dust clouds obscure much of its light. Both galaxies have their own systems of satellites and star clusters, and both contain central supermassive black holes of comparable size. Despite these similarities, the specific patterns of star formation and gas content differ, making each a unique system. Between them stretches about 2.5 million light-years of intergalactic medium, nearly empty space, containing only a few hydrogen atoms per cubic meter. Within that void, faint ultraviolet radiation from the galaxies ionizes the gas, producing a tenuous glow, detectable only with sensitive instruments. This thin bridge of matter connects the two systems' evidence of their shared gravitational domain. The local group's calm motion through the larger universe offers a stable environment for its members. Unlike galaxies in crowded clusters where high-speed collisions are frequent, those here follow slow orbits and maintain their structures for long periods. The relative isolation of this region allows spiral patterns to persist, undisturbed, and thin disks to remain intact. It also reduces the rate of star formation, compared with more active regions, resulting in long-lived balanced evolution. The Large Magellanic Cloud, one of the Milky Way's companions, orbits at a distance of about 160,000 light-years and contains its own sites of ongoing starbirth, such as the Tarantula Nebula. The small Magellanic Cloud farther out is less massive but still gravitationally tied. Streams of gas between them and the Milky Way form the Magellanic Bridge, and the Magellanic Stream long trails extending across hundreds of thousands of light-years. These connections show that even at these vast scales, galaxies exchange matter through tides and outflows, enriching the intergalactic environment. The local group's overall motion toward the Virgo cluster region and the Great Attractor follows the same flow as the entire Laniakea supercluster. Though space expands, gravity inside the group holds firm, preserving its structure against that expansion. Every galaxy within it, including our own, carries billions of stars, planets, and clouds of dust, each orbiting quietly as the group drifts onward through time. From this perspective, the Milky Way's place is both ordinary and serene, one spiral, among many resting within a web of silent neighbours, bound together by gravity's soft hand. Surrounding the visible disk of the Milky Way is an enormous, nearly spherical region known as the galactic halo. It extends far beyond the bright plane of stars, reaching hundreds of thousands of light-years from the centre. This halo is faint and diffuse, composed of dark matter, sparse gas, and isolated stars that drift in slow elliptical orbits. While invisible to the naked eye, its gravitational presence outweighs the luminous disk shaping the motions of stars and satellites throughout the galaxy. Astronomers estimate that most of the Milky Way's mass lies in this unseen component, inferred from how fast stars orbit far from the centre. The dark matter halo likely formed before the visible galaxy, providing the gravitational well into which gas later condensed to form stars and spiral arms. Embedded within this vast sphere are ancient star clusters, some more than 12 billion years old remnants of the galaxy's earliest epochs. These clusters, called globular clusters, orbit far above and below the galactic plane, forming a halo of their own that traces the outer boundaries of the Milky Way's luminous matter. They contain hundreds of thousands of stars packed into volumes only a few dozen light-years across, glowing softly with a yellow or reddish hue that reflects their advanced age. The halo's gas content is extremely low density, amounting to perhaps a few atoms per cubic meter, yet it extends so far that the total mass of this hot, thin medium rivals that of all stars combined. This gas is heated to millions of degrees by ancient supernova explosions and cosmic infall, producing faint X-ray emission detected by space observatories. Around the halo's outer edge, gas flows inward, slowly replenishing the galactic disk and feeding future generations of stars. This quiet circulation connects the Milky Way to the larger intergalactic environment, maintaining a steady balance of matter across cosmic time. The stars in the halo are predominantly old and metal-poor, meaning they formed before many heavy elements existed. Their light carries the chemical signature of a younger universe, when hydrogen and helium dominated and heavier elements were rare. These ancient stars move in random orbits rather than the organized rotation of the disk, giving the halo a spherical rather than flattened shape. Many of them were born in smaller galaxies that the Milky Way absorbed billions of years ago, leaving behind tidal streams, long ribbons of stars stretching across the sky. Modern surveys such as Gaia have mapped these streams with exquisite detail, revealing the ghostly remains of past mergers woven through the halo. Each stream marks the dissolved remains of a once independent system, its stars now part of the Milky Way's extended structure. The largest of these remnants is the Sagittarius stream, formed by the slow disruption of the Sagittarius dwarf galaxy, which continues to orbit and gradually merge with the Milky Way even now. Through such quiet accretions, the halo has grown layer by layer, preserving the memory of each event in its structure. In the outermost regions, where the influence of the galaxy fades into intergalactic space, the halo transitions from bound material to the surrounding cosmic medium. The density of stars there is so low that light from one star may travel hundreds of light years before encountering another. These distant members move under the pull of the galaxy's total mass, their velocities providing crucial evidence for the presence of dark matter. Without this invisible mass, the observed orbital speeds would be far lower, and the outer stars would drift away into space. The halo's existence thus stands as one of the clearest indicators of dark matter's role in galactic formation. It is not static. Subtle motions ripple through it as streams and clumps of matter orbit the center. Computer models suggest that dark matter within the halo forms a complex lumpy distribution rather than a perfect sphere reflecting the history of past mergers and infalling material. The Milky Way's stellar halo is accompanied by a gaseous halo known as the circumgalactic medium. This region acts as a reservoir of baryonic matter, storing material that can eventually cool and fall back into the disk. Observations using ultraviolet light from distant quasars show that this medium extends to at least 200,000 light-years from the galactic center. It contains ionized oxygen, carbon, and other elements spread thinly through hot plasma. Though invisible to the eye, this diffuse gas glows faintly in certain wavelengths, revealing that the Milky Way is surrounded by a vast invisible atmosphere. Within the halo, globular clusters orbit in slow, stable paths that can take hundreds of millions of years to complete. Some of these clusters, such as Omega Centauri, are suspected to be remnants of small galaxies whose cores survived assimilation. Each cluster acts like a fossil, preserving the chemical composition and stellar arrangement of an early cosmic era. The stars within them are nearly as old as the universe itself, shining steadily since long before the sun was born. Their motions help map the galaxy's gravitational potential, offering clues to the mass and shape of the dark halo. The halo's calm isolation contrasts with the busy star-forming regions of the disk. Here time flows slowly and little changes over millions of years. Occasionally a stray cloud of gas falls inward, or a stream of stars passes through, but the general pattern remains one of quiet persistence. The halo's reach even affects the Milky Way's satellite galaxies, guiding their orbits and absorbing material from them over time. The interaction between halo and satellites produces faint bridges of matter that connect the main galaxy to its companions. These bridges, barely visible in optical light, trace the invisible architecture of gravity. The Milky Way's halo is not unique. Every large galaxy possesses one, though each differs in detail depending on its history. Ours happens to be relatively peaceful, with no major collisions in recent billions of years, allowing its structure to settle into balance. The halo's shape is slightly elongated, flattened in the direction of the disk, suggesting a mild influence from rotation. Its total diameter may exceed 1 million light-years when dark matter is included, blending gradually into the surrounding intergalactic medium. Within this vast quiet sphere, the visible galaxy floats like a glowing disk of dust and stars suspended inside a transparent cocoon. The halo's light, faint but persistent, forms the outermost boundary of the Milky Way's luminous body, marking the transition from the familiar night sky to the deep intergalactic dark beyond. Here in this tranquil outer domain, the scale is vast, the density low, and every motion slow, setting the stage for the next inward step toward the galaxy's denser regions where light gathers into spirals. Beyond the faint boundary of the halo, the Milky Way is accompanied by a collection of small satellite galaxies that orbit like quiet companions. These dwarf systems, numbering more than 50, form a loose and uneven cloud of faint light scattered across the sky. Each one is bound to the Milky Way by gravity, yet moves along its own elongated path, some stretching far into the outer halo, before looping back inward again. The largest and most visible of these satellites are the Large and Small Magellanic Clouds, irregular galaxies that can be seen without telescopes from southern latitudes. They glow softly against the night, their diffuse structures connected to the Milky Way by long streams of gas and stars. These streams, collectively known as the Magellanic Stream, extend for hundreds of thousands of light-years, and reveal that even at these scales, galaxies exchange matter through gentle tides of gravity. The Magellanic Clouds are relatively young compared with the Milky Way, containing large regions of ongoing star formation and clouds of hydrogen gas that emit faint radio signals. As they orbit, they pull on the Milky Way's outer disk, creating small ripples and contributing material to its gaseous halo. Their paths are not perfect circles, but irregular loops that evolve slowly as they lose energy and spiral inward over billions of years. Smaller satellites such as the Sagittarius dwarf spheroidal galaxy are in more advanced stages of merging. The Sagittarius system has already been stretched into a long stellar stream that wraps around the Milky Way, evidence of how the larger galaxy grows by absorbing its neighbours. Each dwarf galaxy contributes not only stars but also dark matter and gas, enriching the halo and influencing the galactic disk's future evolution. The faintest satellites, called ultra-faint dwarfs, contain as few as 10,000 stars, and represent the smallest known galaxies. Their low brightness makes them difficult to detect. Many were discovered only recently through deep sky surveys. These systems are dominated by dark matter, with their visible stars forming just a small fraction of their total mass. Their ancient stellar populations suggest that they are among the earliest building blocks of the Milky Way, surviving fragments from the epoch when the first galaxies formed. The distribution of satellites around the Milky Way is not uniform, but arranged roughly along a plane that may reflect the pattern of past accretions. This structure, called the vast polar structure, indicates that many of the dwarf share related orbital histories, perhaps originating from the same group before capture. The gravitational interactions between these satellites and the main galaxy are subtle, but long-lasting, gradually altering the shapes of their orbits and the structure of the Milky Way's outer regions. Each close passage stirs the halo slightly, creating ripples of motion that can persist for millions of years. The Magellanic Clouds, being relatively massive, exert stronger influence. Their combined gravitational pull has likely distorted the Milky Way's outer disk, producing the gentle warp that curves upward and downward beyond the main plane. This effect extends for tens of thousands of light-years, visible through careful mapping of neutral hydrogen gas. Observations with radio telescopes show that the warp rotates slowly, with the disk moving like a vast wave frozen in place. The presence of the clouds may also have triggered waves of star formation in the outer spiral arms, compressing gas as they pass. Though such interactions sound dynamic, the actual motions are extremely slow. A single orbit of the large Magellanic Cloud around the Milky Way may take more than 2 billion years to complete. Between the satellites, space is filled with faint trails of gas and stars torn from their structures by tidal forces. These streams trace elegant arcs across the sky, invisible to the eye but revealed by modern surveys. They form a kind of memory recording the ongoing assembly of the galaxy over time. By studying their shape and velocity, astronomers can reconstruct how the Milky Way grew from smaller pieces, merging quietly rather than through catastrophic collisions. Each dwarf galaxy tells a part of that story, carrying ancient stars that predate the Sun by billions of years. Some, like the Fornax dwarf, contain multiple generations of stars, showing that even tiny systems can sustain star formation over extended periods. Others, like the Sculptor and Draco dwarfs, are more primitive, consisting almost entirely of old red stars that have burned steadily since the universe's early days. The total mass of the Milky Way's satellite system, including dark matter, adds significantly to the galaxy's overall gravitational influence, extending its reach far into intergalactic space. The ongoing discovery of faint satellites continues to refine this picture. Telescopes such as Gaia and the Dark Energy Survey have revealed new members at the limits of detectability, some orbiting hundreds of thousands of light-years away. These discoveries suggest that the Milky Way may have many more companions still hidden within its outer halo waiting to be found. The relationship between the main galaxy and its satellites is one of gradual integration. Over time, tidal forces strip stars and gas from the dwarfs, adding them to the Milky Way's outer regions. The result is a continual process of growth, slow and silent, that has persisted since the galaxy's formation. This mechanism of hierarchical assembly is common throughout the universe, where large galaxies are built from smaller ones over billions of years. Yet within the local group, the Milky Way's environment remains peaceful compared with dense clusters elsewhere. Collisions are rare, and most interactions unfold on timescales too long to disturb the galactic disk's quiet symmetry. The light from the Magellanic Clouds takes about 160,000 years to reach Earth, meaning we see them as they were when early humans first looked up at the night sky. Their presence reminds us that even nearby galaxies are unimaginably distant, yet still connected through the invisible tension of gravity. Each small galaxy, each faint stream of stars, contributes to the Milky Way's complex structure, creating layers of history written in light and motion. From this outer realm of companions, the path now leads inward toward the vast disk itself, where billions of stars orbit in an orderly plane, forming the bright band that defines our galaxy's familiar face. At the farthest visible edge of the Milky Way's luminous body lies the outer disk, where the smooth plane of stars begins to bend and twist. This region, known as the warped and flared disk, forms the boundary between the structured galaxy and the diffuse halo that surrounds it. The disk's warp is gentle yet measurable. As one travels outward along its rim, the galactic plane curves upward on one side and downward on the other, forming a vast wave-like pattern that stretches for tens of thousands of light years. This shape is thought to result from the combined gravitational influence of the Magellanic Clouds and the uneven distribution of dark matter in the halo. Observations of neutral hydrogen gas reveal the warp, most clearly showing that the outermost layers of the Milky Way's disk are tilted by several degrees relative to the inner regions. This subtle distortion means that the galaxy is not perfectly flat, but more like a softly folded sheet, its edges lifted slightly toward the intergalactic dark. The flare of the disk refers to how its thickness increases with distance from the center. Near the Sun, the stellar layer is only a few hundred light-years thick, but at the rim it broadens to several thousand. This gradual expansion creates a delicate gradient between the structured interior and the thin outskirts where stars are few. The outer disk is sparsely populated, its stars scattered, and often older than those nearer the core. Many follow slightly inclined orbits that carry them above and below the galactic plane, adding to the disk's appearance of gentle motion. The gas here is cooler and more tenuous than in the inner regions, composed mostly of atomic hydrogen that emits faint radio waves. These signals have been mapped by large radio telescopes, revealing vast arcs and spurs that trace the structure of the outer galaxy. The overall pattern resembles a vast spiral unfurling into space, its form maintained by rotation and gravity in delicate balance. The Sun itself lies about halfway from the center to the outer edge, some 27,000 light-years inward from the rim. From this vantage, the warp cannot be seen directly, yet it subtly affects the positions and motions of stars in the outer sky. The entire disk rotates once roughly every 230 million years, carrying stars and gas in long, graceful circuits. In the outermost reaches, the rotation speed declines only slightly, a sign that dark matter extends well beyond the visible boundary. This dark halo acts like an unseen scaffold supporting the galaxy's structure and preventing its outer regions from flying apart. Within the warped zone, the density of star-forming regions decreases, but faint traces of new activity remain. Small clusters of young blue stars can still be found born from clouds, compressed by spiral density waves or by the tidal influence of satellites. These distant regions mark the galaxy's limit between ongoing formation and gradual fading. The metallicity of stars, the proportion of the elements heavier than helium, also drops toward the edge, reflecting the lower rate of star birth and chemical enrichment. Here the stars shine with a cleaner light containing fewer traces of past generations. The outer disk is a record of endurance, where ancient stars continue their orbits, largely unchanged for billions of years. Some of these stars, called Cepheids, serve as markers used by astronomers to map the shape and scale of the galaxy. Their regular brightness variations allow precise distance measurements, which reveal the warp's amplitude and direction. Through such studies, the three-dimensional structure of the Milky Way emerges as a dynamic yet stable system, shaped by forces acting slowly over cosmic time. Beyond the edge of the main stellar disk, faint streams of hydrogen gas extend even farther, blending gradually into the halo's circumgalactic medium. These outermost layers represent the transition between the galaxy's organized rotation and the quiet stillness of intergalactic space. They also act as a gateway through which material flows in and out. Gas from the halo drifts inward while outflows driven by supernova winds and radiation pressure move outward, creating a slow, balanced exchange that sustains the galaxy's long-term evolution. The warp itself may oscillate slightly over time, shifting in phase as the gravitational influence of the Magellanic Clouds changes. Computer simulations suggest that these gentle movements occur over hundreds of millions of years so slowly that they would be imperceptible even across the entire span of human history. The stars within the outer disk move at hundreds of kilometers per second, yet the distances are so vast that their positions on the sky barely change in a lifetime. Each one traces a circular path defined by the Milky Way's mass, adding its motion to the grand rotation that unites the galaxy as a whole. The outer disk also contains relics of past mergers, where small satellite galaxies were absorbed and their stars left behind. These remnants appear as faint overdensities or stellar rings looping around the galaxy, like echoes of earlier encounters. The most prominent of these, known as the Monochorous Ring, may represent the remains of a dwarf galaxy disrupted long ago. Its stars follow tilted orbits that intersect the warped outer disk, further shaping its layered appearance. Over time, such remnants blend into the background, their identities lost, as the galaxy smooths itself into equilibrium. Despite its complexity, the Milky Way's outer disk remains a place of quiet stability. The forces acting here are balanced centrifugal motion. From rotation counters the inward pull of gravity, creating a nearly perfect equilibrium that endures for eons. Dust lanes are thin, nebulae are sparse, and the faint light of countless distant stars merges into the soft glow that forms the outer band of the Milky Way visible from Earth on clear nights. From this rim the galaxy's scale becomes most apparent. The span from one side to the other exceeds 100,000 light-years, yet within that expanse all stars move in harmony. The outer warp and flare, though subtle, remind astronomers that galaxies are not rigid structures, but living systems responding to their surroundings. The same gravitational tides that bend the disk also shape the orbits of its satellites and influence the flow of gas throughout the halo. The Milky Way's outer edge is thus both boundary and bridge, linking the stable spiral within to the diffuse domain beyond. As the journey moves inward from this rim toward the thicker, denser layers closer to the galactic plane, the pattern of light grows richer, and the calm of the outskirts gives way to the quiet motion of billions of stars arranged in spirals. Moving inward from the warped rim, the Milky Way thickens into a broader and older structure known as the thick disk. This region extends several thousand light-years above and below the galactic plane, forming a softly glowing layer of ancient stars that envelops the thinner, more active disk inside it. The thick disk is a record of the galaxy's earlier epochs, when conditions were more turbulent and star formation occurred in a denser chaotic environment. The stars here are older, with ages ranging from 8 to 12 billion years, and they contain fewer heavy elements reflecting the chemical composition of the early Milky Way. They shine with a slightly redder hue, their light softened by time and distance. The orbits of these stars are less circular than those in the thin disk. Many move in gentle ellipses that carry them up and down through the galactic plane, creating the thicker appearance. Despite their irregular motions, the overall structure remains remarkably stable, held together by the galaxy's immense gravitational field. The density of stars decreases with height above the plane, fading smoothly into the surrounding halo. The thick disk's origin has long been debated, but evidence suggests it may have formed during a period of intense merging early in the galaxy's history. Collisions with smaller protogalaxies may have stirred the existing stars, puffing up the disk and giving rise to its broader shape. Over time, as conditions calmed, a thinner and more orderly disk developed within it, leaving the thick disk as a fossil of that earlier phase. Chemical analysis supports this view. Stars in the thick disk contain enhanced amounts of alpha elements like oxygen and magnesium products of the first generations of massive stars. These signatures indicate that the thick disk formed quickly before slower processes of enrichment smoothed out the chemical diversity of the younger disk. In the modern Milky Way, the thick disk rotates slightly more slowly than the thin one, a difference of about 30 to 50 kilometers per second. This gentle lag reflects its distinct origin and its higher altitude above the plane. The vertical structure of the thick disk creates a soft glow that envelopes the entire galactic midsection, visible in edge-on views of similar galaxies observed from afar. From such perspectives, the thick disk appears as a faint hazy layer, surrounding a brighter, thinner band of starlight, a pattern that astronomers recognize as a hallmark of mature spiral systems. In the Milky Way, this layer is revealed through statistical studies of stellar motion and composition, rather than direct imaging, since we observe our galaxy from within. The Sun, located roughly halfway between the mid-plane and the edge of the thick disk, moves through this region as part of its orbit around the centre. Every 200 million years or so, it completes one revolution, oscillating gently above and below the galactic plane. The local environment through which it travels is calm, filled with diffuse interstellar gas, sparse clusters and solitary stars. The thick disk acts as a bridge between the ancient halo and the youthful thin disk, preserving traces of both. Some stars here may have originated in smaller galaxies that merged with the Milky Way, while others formed in place during the galaxy's early assembly. Over billions of years, gravitational interactions mixed these populations, blending their properties into the smooth structure observed today. The thickness of this layer, typically around 3,000 light-years, provides resilience against disturbances from spiral arms or passing satellites. Its older stars serve as a stable background against which the more dynamic features of the thin disk unfold. The thick disk also plays an important role in the galaxy's overall balance. By extending vertically, it helps distribute angular momentum and absorb energy from gravitational interactions, maintaining equilibrium across the Milky Way's vast span. In this sense, it functions as a quiet stabilizer, ensuring that the inner disk remains flat and orderly, despite the slow, tidal influences from the halo and nearby companions. The stellar populations of the thick disk tell a story of endurance. Many of its stars have been shining since long before the Earth, formed tracing nearly the entire history of the galaxy. They drift silently through the same orbits their ancestors followed when the universe was less than half its current age. Their light, faint but persistent, contributes to the diffuse background that fills the night sky, merging into the pale band of the Milky Way that arcs across Earth's horizon. Within the thick disk, interstellar matter is scarce. Most of the original gas has long since been converted into stars or dispersed into the halo. The remaining dust forms faint veils through which starlight filters, softening the view. Here, supernova remnants are rare, and the environment is dominated by the quiet presence of old, low-mass stars nearing the ends of their long lifespans. Some of these evolve into white dwarfs, compact remnants that will cool for trillions of years after their light fades. Others continue to burn hydrogen at a steady rate, maintaining stability through slow nuclear fusion. The thick disk contains a few ancient star clusters, survivors from the earliest phases of the Milky Way's assembly. These clusters are sparser than those in the halo, but denser than those in the thin disk, representing a transitional population between the two. Their orbits are inclined, carrying them in sweeping arcs through the galactic plane. By studying their trajectories, astronomers trace the gravitational field of the Milky Way in 3 dimensions, refining estimates of its total mass. The thick disk's structure shows slight asymmetries, subtle ripples that may result from past interactions with satellite galaxies. These features remind us that even this calm region is not static, but slowly evolving. Over the next billions of years, the distinction between the thick and thin disks may blur further, as stellar migration continues to mix populations. Yet for now, the separation remains clear, visible in the differences of chemistry, motion and brightness that define each layer. The thick disk stands as a witness to the galaxy's ancient past, a fossilized relic preserved within the living system of the Milky Way. Above it lies the halo, vast and transparent. Below it spins the thin disk, bright and restless. Together they form a continuum from the oldest stars to the youngest, from the calm outer reaches to the energetic regions of ongoing formation. As the journey continues inward, the stars grow denser, the gas thicker, and the spiral pattern begins to emerge, the elegant geometry that gives the Milky Way its unmistakable form. Deeper within the Milky Way, the thin disk unfolds a broad luminous plain where the majority of the galaxy's stars reside. This region is only a few hundred light-years thick but stretches more than 100,000 light-years across, forming the flat structure that defines the Milky Way's familiar appearance. The thin disk is younger and more active than the thick one, filled with clouds of gas-dark lanes of dust and clusters of bright stars scattered along sweeping spiral arms. Here star formation continues at a measured pace, sustained by the slow rotation of the galaxy and the gravitational waves that compress gas into new suns. The disk's structure is not rigid but fluid, shaped by the balance of rotation and gravity. Every star, from the faintest red dwarf to the most luminous blue giant, follows an orbit around the galactic center, moving together in a vast rotation that keeps the system coherent. The orbital speed near the Sun's position is about 220 kilometers per second, meaning that each complete rotation takes roughly 230 million years. Despite this enormous motion, the stars appear fixed from our vantage point because of the immense scale. The thin disk is organized into spiral patterns, long curved arms that wind gracefully outward from the central region. These arms are not solid structures but density waves, slow-moving compressions that sweep through the disk and temporarily concentrate gas and stars. As gas enters these regions, it is compressed, triggering the birth of new stars. When it leaves, the gas expands again, leaving behind clusters that drift quietly in its wake. The spiral pattern moves at a different speed from individual stars, so that over time stars drift in and out of the arms like swimmers passing through gentle waves. The Milky Way's overall structure is that of a barred spiral, meaning that a central bar-shaped region of stars extends across its core from which the arms emerge. Observations using infrared telescopes have revealed this bar clearly, along with at least 4 major arms: the Scutum Centaurus arm, the Perseus arm, the Sagittarius arm, and the outer arm. The Sun lies near a smaller feature called the Orion Spur, situated between the Sagittarius and Perseus arms. This position offers a relatively quiet location, away from the crowded regions near the galactic center, but close enough to observe much of the galaxy's structure. The thin disk contains not only young stars but also the interstellar medium, an intricate mix of gas dust and magnetic fields that fills the space between them. Roughly 10% of the disk's mass resides in this medium, which exists in multiple phases: cold molecular clouds, warm neutral gas, and hot ionized regions. Each phase interacts with the others through slow cycles of heating, cooling, and compression. This dynamic balance maintains the galaxy's ability to form stars while preventing collapse. Dust grains within the interstellar medium absorb and scatter, light producing the dark patches that thread the Milky Way's bright band. These grains also provide surfaces where complex molecules can form, including water, carbon monoxide, and organic compounds. The thin disk's chemical composition reflects billions of years of evolution. Supernova explosions enrich the gas with heavier elements, while stellar winds recycle material back into space. As a result, new generations of stars form from gas that contains traces of earlier ones. This continuous recycling gives the thin disk a higher metallicity compared with the thick disk or halo marking it as the galaxy's most mature layer. The thin disk also hosts planetary systems in abundance. Around the Sun's orbit, astronomers estimate there may be tens of billions of planets, many orbiting stars similar to our own. Within the dense lanes of the spiral arms, the probability of such systems increases further, as star formation is most active there. Yet even with so many stars, the average distance between them remains vast, several light years, leaving space mostly empty and serene. From within the thin disk, the night sky glows with the combined light of billions of stars seen edge on through the galactic plane. This view, visible from Earth on a dark night, appears as a soft band of light stretching across the heavens. The thin disk's stars follow nearly circular orbits, maintaining the flatness of the structure through the stabilizing influence of angular momentum. Small oscillations up and down through the mid-plane give the disk its subtle thickness, while large-scale patterns such as ripples caused by past satellite interactions add texture without disrupting its overall form. The balance of gravity, motion and pressure ensures long-term stability even as stars come and go. Near the Sun, the stellar population includes all spectral types, from massive short-lived blue stars to faint ancient red dwarfs, reflecting the disk's continuous history of formation. Young clusters dot the spiral arms, their members still bound by gravity, while older clusters gradually disperse into the field as their stars drift apart. The thin disk's average density declines slowly with distance from the center, creating a smooth radial gradient in brightness and chemical composition. Closer to the core, stars are richer in heavy elements. Farther out, they grow poorer in metals, echoing the pattern of gradual enrichment over time. Embedded within this structure are open clusters, small groups of stars formed from the same cloud. These clusters serve as natural laboratories for understanding stellar evolution. Over tens of millions of years, they dissolve into the general background, adding their members to the galaxy's ever-changing tapestry. The interstellar magnetic field, though weak, threads through the disk and guides the flow of charged particles. Cosmic rays travel along these lines, carrying energy across great distances and influencing the temperature of the surrounding gas. The interplay of magnetic fields, gravity and rotation creates a complex but balanced system, one that evolves slowly without disturbing the disk's overall calm. The thin disk's appearance from afar would resemble a luminous rotating plate of starlight crossed by dark lanes of dust and encircled by a faint halo. Its luminosity dominates the Milky Way, producing most of the visible light that reaches observers on Earth. Within it, the Sun continues its slow orbit around the center, following a path shared by countless other stars that together define the galaxy's smooth rotation curve. The thin disk is both the Milky Way's most active and most familiar region, the part we inhabit, the layer that holds the Sun, the Earth, and the quiet blue sky. Yet despite its relative proximity and familiarity, it remains vast beyond comprehension. Each small region of it, even one, 1,000 light-years across, contains more stars than can be counted, each with its own planets, histories and potential. As we move inward along this broad and glowing plane, the density of light will increase, and the spiral structure will soon give way to the crowded brilliance of the inner arms and the galactic bar that leads toward the center. Within the thin disk, the Milky Way's spiral pattern becomes more distinct, revealing its elegant geometry of arms and spurs. These immense structures are not rigid but rather transient waves of density that move slowly through the galactic disk, shaping the flow of stars and gas without holding them permanently in place. The major spiral arms define the visible framework of the galaxy: the Scutum Centaurus arm, the Perseus arm, the Sagittarius arm, and the outer arm. Between them lie smaller spurs, including the Orion spur, where the Sun resides, bridging the gap between two great arms. Each arm contains billions of stars and stretches across tens of thousands of light years, illuminated by clusters of young blue giants and threaded with dark lanes of dust. The Scutum Centaurus arm begins near the central bar and curves outward across the southern sky, a vast ribbon of light extending nearly halfway around the galaxy. It is rich in star-forming regions where molecular clouds collapse under gravity to create new stellar clusters. The Perseus arm lies on the far side of the Milky Way, slightly beyond the Sun's orbit, and marks one of the outermost major features. Its luminous associations of young stars make it a beacon across the galactic disk. The Sagittarius arm, closer to the centre, crosses the line of sight from Earth, filled with bright nebulae such as the Eagle and Lagoon nebulae. These are places where ultraviolet radiation from newly formed stars excites surrounding gas, producing diffuse glows of red and blue light. The outer arm, fainter and more distant, traces the edge of the stellar disk, where the warp begins to rise. Together, these arms form the graceful spiral that gives the Milky Way its characteristic shape, though from inside the pattern appears diffuse and complex. The Orion Spur. Our local feature is a smaller segment connecting two of the larger arms. It contains the Sun, the solar system, and many nearby star clusters. From within this spur, astronomers view the Milky Way edge-on, seeing the combined glow of countless stars spread along the plane. The spiral arms rotate at a pattern speed slower than the orbital speed of stars, which means stars move in and out of them over time. This differential motion ensures that the pattern endures even as individual stars change positions. The density waves themselves are thought to arise from instabilities in the disk's rotation, or from gravitational influences of the central bar and satellite galaxies. Whatever their precise origin, the arms represent areas where matter is slightly more concentrated enough to trigger bursts of star formation as gas is compressed. These newborn stars then illuminate their surroundings before dispersing into the general field. Each spiral arm acts as both nursery and archive, holding generations of stars at different stages of life. The colour gradients within them tell a story of time. The brightest blue stars mark the newest clusters, while redder regions host older populations that have drifted away from their birth clouds. The arms also host vast complexes of interstellar dust and gas, nebulae, molecular clouds, and supernova remnants that together form the texture of the galactic disk. Some of these clouds span hundreds of light years and contain enough material to form millions of suns. They are threaded by magnetic fields and stirred by turbulence, yet their overall behavior remains calm on galactic scales. Within them, gravity slowly gathers matter into dense cores, beginning the process that will one day ignite new stars. The spiral pattern is also visible in the distribution of older stars, though less distinctly. These ancient populations reveal that the arms are not only sites of new formation, but long-standing features guiding the dynamics of the disk. The gas stars and dust together create a self-sustaining rhythm. As density waves pass, they trigger star formation, and the resulting feedback from young stars shapes the surrounding gas, influencing the next generation. This cyclic behavior maintains the galaxy's structure over billions of years. The bar at the Milky Way's center contributes to the spiral geometry by driving waves outward through gravitational resonance. Extending roughly 27,000 light-years across, the bar rotates slowly, funneling gas toward the core and helping sustain both the spiral arms and the central molecular zone. Observations in infrared light, which can penetrate the dust of the inner regions, show that the bar is made of older reddish stars arranged in a slightly twisted shape. Its presence gives the galaxy a mild asymmetry, with arms emerging from each end at different angles. From our position near the Orion Spur, these structures blend into one another, creating the mottled appearance of the Milky Way's band across the night sky. Embedded within the arms are many open clusters, loose associations of stars born together from the same cloud. These clusters are temporary gatherings that disperse over hundreds of millions of years. Their distribution along the spiral arms highlights the ongoing nature of star formation. Some of the brightest clusters visible from Earth, such as the Pleiades and the Hyades, lie within the Orion spur, providing nearby examples of the processes that shape the entire galaxy. Alongside them are massive stellar associations and OB groups, collections of hot luminous stars that illuminate their surroundings with intense ultraviolet light. The energy from these stars sculpts nearby gas into intricate forms, creating emission nebulae and bubble-like cavities. Over time, supernova explosions from the most massive stars enrich the surrounding gas with heavy elements, contributing to the chemical evolution of the disk. The spiral arms also serve as channels for galactic rotation, guiding streams of gas toward the center and maintaining the overall angular momentum. The pattern is dynamic but enduring a system of motion, in which billions of stars participate without collision. Between the arms, interarm regions are quieter, filled with older stars and diffuse gas. These zones act as reservoirs where material can cool before rejoining the next wave of density. The alternation between arm and interarm regions gives the disk its texture and balance, like alternating currents within a calm sea. From above, the Milky Way would appear as a glowing pinwheel of soft light, with the arms marked by brighter, bluer regions, and the gaps between them tinged with faint yellow. The symmetry is not perfect. Spirals are always slightly irregular, but the overall harmony of form remains clear. The presence of spiral arms is one of the galaxy's defining characteristics, linking its vast scale to the delicate physical processes that occur within individual clouds. The same rotation that holds planets in orbit around stars also governs the motion of the arms around the galactic center. Every element, from the smallest dust grain to the largest cluster, moves according to the same gravitational rhythm. As the perspective continues inward along the spiral pattern, the density of stars increases and the light grows warmer. The quiet outer regions give way to the crowded interior, where the spiral arms begin to merge into the bar and the interstellar medium thickens into the bright heart of the galaxy. Between the stars of the Milky Way lies an immense and intricate substance known as the interstellar medium, the quiet ocean of gas and dust that fills the space within the galactic disk. It is this medium that gives the galaxy its living texture, providing the material from which stars are born and to which they eventually return their matter. Though it appears empty, the interstellar medium is rich in structure, composed of multiple phases that coexist in a delicate equilibrium. About 90% of it is gas, mostly hydrogen, and the remaining fraction consists of fine dust grains made of silicates, carbon compounds, and traces of ice. These particles are small enough to float freely, each no larger than a fraction of a micron, yet collectively they absorb and scatter starlight, creating the dark lanes that thread the Milky Way's spiral arms. The density of this medium is extraordinarily low, averaging only a few atoms per cubic centimetre, but the volume it occupies is so vast that its total mass equals several billion times that of the Sun. Within this medium exist distinct layers of temperature and density shaped by the flow of energy through the galaxy. The coldest and densest regions are molecular clouds, where hydrogen atoms pair up into molecules and temperatures drop to only a few tens of degrees above absolute zero. These clouds are immense, some spanning hundreds of light years, and containing enough material to form entire clusters of stars. Surrounding them is a warmer layer of neutral gas, more diffuse but still substantial, which emits radio waves detectable across the disk. Above and between these cooler regions lies hot ionized gas at millions of degrees, produced by supernova explosions and energetic stellar winds. The balance between these components creates a dynamic yet stable ecosystem maintained by the constant exchange of heat and pressure. Energy flows through the interstellar medium in slow cycles. Massive stars inject radiation and shock waves that heat the surrounding gas, while cooling processes allow denser regions to condense and collapse. The dust particles, though small, play a crucial role by shielding molecular clouds from intense ultraviolet light and enabling chemical reactions on their surfaces. Molecules such as carbon monoxide, water, and formaldehyde form within these protected interiors, marking the first steps toward complex chemistry. Observations in infrared and radio wavelengths reveal filaments, bubbles, and shells within the medium carved by ancient stellar events. Each structure evolves over millions of years, expanding, merging, or dissipating into the surrounding space. Despite these changes, the overall density of the interstellar medium remains nearly constant when averaged across the galaxy. Gravity, radiation, and magnetic fields act together to maintain this long-term balance, preventing the collapse of the disk or its evaporation into the halo. Magnetic fields, though weak compared with gravity, weave through the interstellar medium like invisible threads, aligning the motion of charged particles and shaping the orientation of dust grains. These fields can trap cosmic rays, high-energy particles that travel through the galaxy at nearly the speed of light, creating a diffuse background of radiation. Cosmic rays ionize gas-influenced chemical reactions and contribute to heating the medium in subtle ways. The interplay between magnetism and turbulence produces intricate patterns seen in polarized light that traces the alignment of dust. Within this seemingly tranquil expanse, stars act as both creators and destroyers. When a massive star forms, it emits strong winds that clear cavities in the surrounding gas, forming vast bubbles tens of light years across. When that star reaches the end of its life and explodes as a supernova, it releases enormous energy that stirs and enriches the surrounding space. The heavy elements produced in these explosions, carbon-oxygen ion, mix into the interstellar medium, ensuring that future generations of stars and planets contain the raw materials for complex chemistry. This enrichment process, gradual and unending, gives each new star a slightly higher metallicity than its predecessors. The interstellar medium thus acts as the galaxy's circulatory system, redistributing matter and energy through every part of the disk. The life cycle of stars depends entirely on this medium, and in turn it depends on the stars to maintain its renewal. Over millions of years, supernova remnants fade, their shock waves dissipate, and the gas cools to form new clouds. The cycle repeats endlessly, preserving the Milky Way's vitality. Between major spiral arms, the interstellar medium becomes more diffuse, forming wide regions of lower density, where radiation travels farther and cooling is slower. These interarm zones contain relic clouds and faint filaments connecting larger structures. They act as buffers, ensuring that the bursts of star formation in the arms do not consume all available gas at once. In the outer disk, the medium thins even further, merging with the circumgalactic gas of the halo. Their cold clouds and hot plasma coexist at the galaxy's boundary, showing that the interstellar medium has no sharp edge, but fades gently into the surrounding darkness. Dust within the medium scatters blue light more efficiently than red, which is why the Milky Way's glow appears warm and golden when viewed from Earth. This selective scattering also reddens the light from distant stars, providing clues to the density and distribution of dust along the line of sight. Observations by satellites such as Planck and Herschel have mapped this dust across the entire sky, revealing swirling patterns shaped by turbulence and magnetic fields. Each filament and wisp marks the invisible movement of gas over timescales that stretch far beyond human perception. The calm appearance of the night sky conceals these slow motions where entire clouds drift at a few kilometers per second, taking millions of years to traverse even small portions of the galaxy. The temperature and pressure differences between regions drive gentle flows of material, while rotation adds subtle shear that stretches structures into long arcs. These processes operating together sustain the Milky Way's disk as a living, self-regulating system. Despite its complexity, the interstellar medium remains remarkably efficient at maintaining equilibrium. The rate at which stars form about 1 to 2 solar masses per year matches the replenishment of gas from stellar winds and supernovae. This steady state has persisted for billions of years and is likely to continue for billions more. Without this delicate balance, the galaxy would either exhaust its gas too quickly or remain inert without new stars to replace the old. The interstellar medium ensures continuity, connecting the galaxy's past and future through the slow exchange of matter. Seen from above, the Milky Way would appear as a glowing spiral embedded in faint veils of gas and dust. The interstellar medium would trace its arms in soft hues of red and blue, illuminated by starlight filtering through translucent clouds. In this vast, quiet ocean, every atom and grain contributes to the gentle rhythm of creation and decay that defines the galaxy. The airless void between stars is not empty but alive with motion, light, and memory, carrying the imprint of billions of years of cosmic evolution. Inside the broad flow of the interstellar medium, certain regions become so dense and cold that they begin to collapse under their own gravity. These are the star-forming regions of the Milky Way vast molecular clouds, where the quiet process of stellar birth unfolds. They are among the calmest and yet most vital structures in the galaxy, hidden within dark nebulas that block visible light but glow faintly in infrared and radio wavelengths. Each cloud contains enormous quantities of molecular hydrogen mixed with traces of helium, carbon, and oxygen. The gas within them cools to only a few tens of degrees above absolute zero, allowing gravity to dominate over internal pressure. Over time, small fluctuations in density amplify leading pockets of gas to condense into compact knots. These knots or cores mark the earlier stages of star formation. As they collapse, their centers heat up until nuclear fusion ignites, transforming invisible clumps of gas into shining stars. The entire process may take millions of years, yet when viewed on a galactic scale it is continuous and gentle, maintaining a steady rate of new stellar creation across the disk. Star-forming regions are often found along the spiral arms, where density waves compress gas into long filaments and clusters. One of the best known is the Orion Molecular Cloud Complex, a vast region spanning hundreds of light years and containing the Orion Nebula, a stellar nursery visible even to the unaided eye. Within such nebulae, thousands of young stars illuminate the surrounding gas, producing colourful emission patterns in shades of red and pink. The ultraviolet radiation from these new stars carves cavities in the clouds, sculpting them into pillars and arcs. Another prominent region lies within the Carina Nebula, where massive stars cluster in dense groups, their winds driving shock fronts through nearby gas. Similar formations occur throughout the Milky Way, though most are obscured by dust and visible only to instruments sensitive to longer wavelengths. Within these clouds, stars often form in groups rather than alone. The reason lies in the nature of turbulence. The same chaotic motions that cause density fluctuations also fragment clouds into multiple cores. Each core becomes a potential star system, and the surrounding filaments feed material into them as they grow. Many of the galaxy's most massive clusters originated this way, born from giant molecular complexes containing millions of solar masses of gas. The efficiency of this process is low. Only a small fraction of the total gas becomes stars before feedback halts further collapse. Stellar winds radiation pressure, and eventually supernova explosions disperse the remaining gas, ending the cycle in that region. The newly formed stars then drift away as the cluster dissolves, spreading young populations throughout the disk. This constant replenishment ensures that the Milky Way maintains its mix of stellar ages, from ancient red giants to luminous blue newcomers. The conditions for star formation depend strongly on the balance between gravity and turbulence. If the gas is too warm or diffuse, it resists collapse. If it is too cold, fragmentation proceeds rapidly. Magnetic fields add further complexity, guiding the flow of matter and delaying collapse in some regions, while accelerating it in others. Observations of nearby molecular clouds show intricate networks of filaments only a few light years across, threaded by magnetic lines and dotted with dense cores. These filaments appear universal across galaxies, suggesting that the basic mechanisms of star formation are the same everywhere. In the Milky Way, thousands of such clouds populate the spiral arms, creating a patchwork of activity. At any given time, dozens of massive clusters are forming across the disk, though each process remains hidden within thick curtains of dust. Infrared telescopes such as Spitzer and Herschel have revealed these regions in detail, showing that star formation is not uniform but episodic flaring where conditions align. On average, the Milky Way forms about 1 or 2 new solar masses of stars each year, an equilibrium maintained by the supply of gas from the halo and by the return of material from dying stars. This slow rate ensures stability, avoiding the bursts that can exhaust a galaxy's fuel too quickly. Within the most massive star-forming regions, clusters of hot, short-lived stars produce intense radiation that shapes the surrounding medium. These stars, often tens of times more massive than the Sun, live only a few million years before ending as supernovae. Their explosions enrich nearby gas with heavy elements, seeding future generations of stars and planets. The interplay of destruction and renewal keeps the galaxy chemically evolving, gradually increasing the abundance of elements necessary for rocky worlds and life. The remnants of these events, expanding shells of gas called superbubbles, merge with the surrounding interstellar medium, driving gentle turbulence through the disk. Smaller stars like the Sun form more quietly and live far longer. They emerge from less massive cores, shedding their natal clouds without violent feedback. Around many of them, leftover dust forms rotating disks that can eventually condense into planets. The distribution of such protoplanetary disks within the Milky Way is vast. Nearly every region of recent star formation hosts thousands of them. Observations from the Gaia and ALMA observatories show that planet formation begins early, often while the young star is still gathering material. These quiet processes unfold unseen, scattered through the galaxy's arms, contributing to the slow accumulation of planetary systems. The energy released during star formation also influences the surrounding interstellar medium. As radiation escapes from newborn clusters, it heats nearby gas and prevents further collapse, creating a self-regulating mechanism. This feedback ensures that no part of the disk forms stars faster than the available gas supply allows. Over long timescales, the combined effect of thousands of such regions shapes the structure and brightness of the Milky Way's arms. From a distance, a galaxy in this phase would appear balanced, glowing softly with the light of intermediate-age stars while dotted with bright knots where new ones are forming. The Milky Way, being a mature spiral, sits in this steady stage of life. Its star-forming regions are neither rare nor excessive, spread evenly enough to maintain harmony between creation and depletion. The gas that fuels them flows slowly inward from the halo, replenishing the disk as older stars die. The faint glow of these regions, combined with the diffuse reflection of light from dust, gives the Milky Way its gentle luminosity when seen edge-on from afar. Within each cloud, the birth of a star is a quiet transformation, a subtle rearrangement of matter under gravity's guidance. No sudden light bursts across the galaxy. Instead, the process unfolds silently, adding another point of light to the collective radiance of the disk. Over billions of years, such modest acts of creation have built the galaxy's vast population of stars, ensuring that even as old systems fade, new ones will always rise to replace them. Among the calm patterns of gas and stars that fill the Milky Way, there exist bound families known as open clusters and stellar populations groups that reveal the galaxy's slow evolution through time. Open clusters are loose gatherings of stars formed from the same cloud of gas, sharing nearly identical ages and chemical compositions. They range from just a few dozen members to several thousand, held together by mutual gravity for a limited time before dispersing into the wider disk. These clusters are scattered mainly along the spiral arms tracing regions of recent star formation, like beads of light woven through the galaxy's lanes. The youngest examples, such as the Pleiades and NGC 6530 in the Lagoon Nebula, shine with bright blue stars that have existed for only tens of millions of years. Older clusters like M67 or NGC 188 are much dimmer and redder survivors that have persisted for billions of years as the rest have dissolved. The life of a cluster follows a gentle arc. It begins when a cloud collapses into many stars at once, then slowly expands as gravitational interactions between members push them apart. Over hundreds of millions of years, tidal forces from the Milky Way stretch the cluster's boundaries until its stars drift away, joining the background population of the thin disk. In this way, the galaxy is constantly mixing its stars, blending the contributions of countless former clusters into a smooth distribution. Every star in the night sky likely began as part of such a family now long scattered. The chemical unity within each open cluster allows astronomers to trace their origins. By comparing their elemental abundances and motion, one can reconstruct the history of the Milky Way's star-forming regions. This field, known as galactic archaeology, reveals how stars migrate through the disk over time. Many older clusters now orbit far from where they form their positions, altered by the slow diffusion of orbits caused by spiral density waves and gravitational interactions. The Sun itself may have formed within an open cluster nearly 5 billion years ago, its siblings now dispersed across the galaxy. Somewhere among the faint stars of the disk, traces of that original family still exist, indistinguishable to the eye, but connected through shared chemical fingerprints. Beyond the clusters, the Milky Way's stellar populations exhibit a wide range of ages and compositions. The younger stars are massive and luminous, concentrated in the arms where gas is abundant. Their short lives ensure they remain close to their birthplaces, contributing blue light to the spiral structure. Mid-age stars like the Sun are distributed throughout the disk, orbiting the center in near-circular paths. The older stars, faint and reddish, populate both the thick disk and halo, preserving the memory of the early galaxy. Together they form a continuum spanning the galaxy's entire history, from the first stars formed over 12 billion years ago to those still igniting today. The distribution of these populations follows gradients that reveal the slow chemical evolution of the Milky Way. Closer to the center, stars contain higher metallicity, enriched by many cycles of formation and supernovae. Farther out, the abundance of heavy elements declines, showing that the outer disk has undergone fewer generations of enrichment. The study of these gradients provides a timeline of how the Milky Way assembled its matter from inside outward. The smooth mixing of stellar populations gives the galaxy its tranquil appearance. Though billions of stars orbit independently, their combined light forms a steady glow without visible change. Each population contributes differently to this radiance. Young stars dominate the spiral arms, intermediate ones shape the disk's background, and ancient stars fill the halo with a faint, steady halo of light. The interplay between these groups maintains the galaxy's visual balance and internal stability. Open clusters also act as markers of the Milky Way's rotation. Their distances and velocities allow astronomers to map the galaxy's structure and measure the rate at which different regions orbit the center. Observations show that the disk rotates nearly as a solid body in its inner parts, but flattens into a constant speed beyond the solar circle, a result explained by the presence of dark matter. The stars of various ages move within this gravitational field, their orbits gently perturbed by the passage of spiral arms and nearby molecular clouds. These perturbations cause slow radial migration stars drifting gradually inward or outward over billions of years, blurring the boundaries between populations. Through this process, the Milky Way remains dynamically alive, its stars continually exchanging places without disrupting the galaxy's overall harmony. The presence of clusters also enriches the interstellar environment. As stars evolve within them, winds and supernovae return gas to space, seeding nearby clouds with fresh material for new generations. This exchange keeps the chemical evolution of the disk continuous. The rate of this recycling determines the metallicity distribution that astronomers observe today. Young clusters in the inner arms tend to have higher metallicities than those farther out, mirroring the pattern of gradual enrichment that has unfolded since the galaxy's birth. Stellar populations are not evenly distributed vertically either. Younger stars are concentrated near the mid-plane, while older ones occupy greater heights in the thick disk. This vertical layering produces the smooth luminosity gradient seen in edge-on views of the Milky Way. Between these layers, faint traces of past events remain ripples and waves, produced by interactions with satellite galaxies or by fluctuations in the disk's own gravity. These features remind us that the galaxy, though serene, is never truly still. Each motion, each subtle shift contributes to the slow reorganization of its billions of members. In the solar neighborhood, the stellar density is about 1 star per cubic parsec, or roughly 30 light-years between typical stars. Despite such vast separation, the combined gravitational influence of all these objects keeps the disk coherent like a flock moving together through the dark. Among these populations, some stars are solitary, while others exist in binaries or small systems. Such diversity adds texture to the Milky Way's structure, but does not disturb its calm equilibrium. Over time, gravitational encounters redistribute kinetic energy, ensuring that stars of different masses and ages share similar velocity patterns. This equilibrium state gives the galaxy its long-term stability, allowing it to persist with little change over cosmic timescales. Observations from Gaia have transformed our understanding of these populations, providing precise positions and motions for more than 1 billion stars. The resulting map reveals the Milky Way as a gently rotating disk with subtle patterns of streaming and oscillation. Embedded within these patterns are clues to past mergers, spiral density waves, and tidal interactions that shape the current configuration. Yet even with this complexity, the overall impression remains one of quiet order. The Milky Way's stars, whether young or ancient, bright or faint, participate in a collective motion that has continued unbroken for billions of years. Each open cluster that dissolves, and each star that drifts away, becomes part of this larger harmony. In the combined light of these populations, the galaxy sustains its steady glow, serene and unhurried, a single organism composed of countless lives. Far beyond the scattered open clusters and the young stars of the thin disk lies another ancient domain of the Milky Way, the realm of the oldest stellar populations and the great globular clusters that orbit like remote lanterns around the galactic halo and bulge. These systems represent the most ancient surviving structures from the galaxy's formation, relics of an age when the Milky Way was still assembling from smaller protogalactic fragments. Globular clusters differ profoundly from the open clusters of the spiral arms. They're densely packed spheres containing hundreds of thousands, sometimes millions of stars confined within regions only a few tens of light-year across. Their cores are among the most crowded stellar environments in existence, where stars lie so close together that their gravitational fields overlap. Despite this density, the clusters are tranquil, having reached equilibrium after billions of years of slow internal motion. The stars inside them are almost all ancient, with ages exceeding 12 billion years, making them nearly as old as the universe itself. Their light is typically yellow or reddish, rich in evolved giants, and devoid of the massive blue stars that live only briefly. Observations have revealed more than 150 such clusters orbiting the Milky Way, forming a loose spherical distribution that extends far beyond the visible disk. Each cluster follows its own elongated path around the galactic center, some plunging through the disk, and others remaining in distant orbits reaching hundreds of thousands of light-years into the halo. They act as gravitational beacons tracing the shape of the galaxy's potential, and by studying their motions, astronomers can measure the mass of the Milky Way's unseen dark matter halo. Many globular clusters may have originated outside the Milky Way, brought in by the slow merging of smaller galaxies. Their differing chemical compositions suggest diverse origins, each one preserving the record of a distinct environment, long since absorbed into the larger system. Over time, tidal forces have stripped stars from some clusters, producing thin streams that now weave through the halo. These streams, like those of the Sagittarius dwarf galaxy, form intricate networks that tell of a history of gentle accretion rather than violent collision. The clusters that survive today are the most resilient remnants of those early times, bound tightly enough to resist the disruptive pull of the galaxy for billions of years. Inside a typical globular cluster, the stars orbit in all directions, forming a roughly spherical distribution. Collisions between stars are rare despite the density because their relative motions are high, but close encounters do occur, occasionally leading to the formation of exotic objects such as blue stragglers, stars that appear younger and hotter than the rest, likely formed by mergers or mass transfer in binary systems. The dynamics of these clusters evolve slowly through two-body relaxation, a process where repeated gravitational interactions gradually redistribute energy among stars. Over immense timescales, heavier stars sink toward the center, while lighter ones drift outward, a phenomenon known as mass segregation. The overall structure, however, remains remarkably stable. Some clusters contain evidence of multiple stellar populations, showing that they may have experienced more than one episode of star formation in their early history. This discovery has reshaped understanding of how such dense systems formed, suggesting that they may once have been the cause of small galaxies captured by the Milky Way. One of the largest examples, Omega Centauri, is thought to fit this description, containing distinct populations of stars with different ages and metallicities. Its mass exceeds 4 million solar masses, and its flattened shape hints at a complex past. Other clusters, such as M13 in Hercules or 47 Tucanae in the southern sky, are smaller but equally ancient, shining as dense spheres of golden light when observed through telescopes. Their collective distribution defines a roughly spherical halo around the Milky Way, extending out to distances where the galaxy's rotation gives way to the quiet of intergalactic space. The total mass contained in globular clusters is only a small fraction of the galaxy's total, yet their importance as fossils of formation is immense. Each one provides a window into the early conditions of the universe, preserving stars that formed before heavy elements were abundant. The average metallicity of these stars is low, indicating that they were born before supernovae had enriched the interstellar medium with metals. By studying them, astronomers can trace the timeline of chemical evolution from the first generations of stars onward. These clusters also serve as natural laboratories for understanding stellar evolution under extreme density. Because all their stars are roughly the same age and composition differences in brightness and colour reveal clear sequences on the Hertzsprung-Russell diagram, allowing precise determination of their ages. The discovery that the oldest globular clusters are around 13 billion years old set an important lower limit on the age of the universe, long before cosmological measurements confirmed similar values. Surrounding the dense inner clusters of the halo is a population of isolated ancient stars not bound to any group. Many of these halo stars move in elongated orbits that carry them far above and below the galactic plane. Their chemical simplicity, some with iron, abundance is less than 1,000th that of the Sun, shows that they formed from nearly primordial material. These are among the first stars born after the Big Bang, survivors of an era when the galaxy itself was still forming from collapsing clouds of gas. Their presence provides direct evidence that the Milky Way's assembly was a gradual process, building layer upon layer through the merging of smaller systems. Within the inner halo, the density of globular clusters increases toward the galactic bulge, forming a transition zone between the old halo and the dense core. Here, the gravitational field is strong, and clusters orbit rapidly, completing circuits in only a few 100 million years. Some of these inner clusters are partially obscured by dust visible only in infrared light. Their proximity to the center exposes them to tidal forces that can distort their shapes, stretching them slightly along their orbital paths. Despite these stresses, most remain intact, their stars bound by deep gravitational wells. The slow evaporation of stars from the outer layers contributes to the halo's population of isolated ancient stars, blending the boundaries between cluster and field. The Milky Way's globular clusters collectively form one of its most symmetrical and stable components, enduring while the disk rotates and evolves. They represent the memory of a time when the universe was young, when galaxies were assembling, and the first heavy elements were being forged. Their persistence over cosmic history demonstrates the long-term equilibrium that gravity can create, turning chaos into quiet structure. From these high ancient orbits, the view of the galaxy below would be serene, a glowing spiral disk surrounded by the faint shimmer of the halo, a luminous whirlpool of stars slowly turning in the dark. As the journey now moves inward from these ancient outer sentinels toward the heart of the Milky Way, the density of light and matter will rise dramatically, leading into the bright, crowded realm of the galactic bulge. Closer to the Milky Way's heart, the scattered order of the spiral arms gives way to a dense, rounded region known as the galactic bulge. This is the central swelling of the galaxy, a thick concentration of stars that stretches for tens of thousands of light years around the core. From Earth's position in the disk, the bulge appears as a bright golden haze at the center of the Milky Way, partially veiled by dark lanes of dust. In structure, it is not a perfect sphere, but a flattened, boxy form with the bar running through its center, blending seamlessly with the inner ends of the spiral arms. The bulge contains some of the oldest stars in the galaxy, mixed with younger populations formed from gas funneled inward by the bar. The result is a complex environment of overlapping ages, motions, and compositions. The stars here move in intricate orbits, some tracing elongated paths along the bar, others looping in random directions. Their combined motion creates the bulge's thick lens-like appearance when viewed edge-on. This region holds roughly a quarter of the Milky Way's stellar mass, packing tens of billions of stars into a space only a few thousand light-years across. Because of this density, the night sky from within the bulge would be bright and crowded with hundreds of stars visible in every direction. Yet despite this apparent brilliance, the overall scene remains calm, the product of countless independent motions balanced by gravity. The light from the bulge is dominated by yellow and red hues characteristic of evolved stars such as red giants. These stars are nearing the ends of their lives, having exhausted hydrogen in their cores and expanded to large cool surfaces. Their collective glow gives the bulge its warm colour, contrasting with the bluer tones of the spiral arms. Among them lie smaller numbers of younger, hotter stars, evidence that star formation still occurs sporadically in this region. The gas required for this activity is drawn inward from the disk along the bar, where gravitational torques channel material toward the centre. This slow inflow sustains modest star formation, even as most of the original gas has long been converted into stars. The overall metallicity of the bulge is higher than that of the outer disk, showing that it has experienced many generations of star birth and supernova enrichment. However, variations exist within it. Stars in the inner bulge tend to be older and more metal-rich, while those farther out include slightly younger populations. These gradients suggest a complex history in which rapid early formation was followed by periods of quiet accretion and renewal. Observations using infrared telescopes, which can pierce the dust that obscures visible light, have revealed the bulge's fine structure in remarkable detail. Its shape resembles an elongated peanut or an X when viewed from certain angles, an effect created by the bar's vertical buckling. This feature is not unique to the Milky Way. Many spiral galaxies display similar bulges, the result of internal instabilities that lift stars above and below the plane. The motions of stars within the bulge confirm this pattern, showing that the bar and bulge form a single coherent structure, rotating together around the galactic center. The rotation speed here is high, with stars completing orbits in a few tens of millions of years. Despite this, collisions between stars remain exceedingly rare because of the vast distances separating them. The gravitational potential of the bulge is deep, binding the inner regions tightly and influencing the orbits of stars far out in the disk. This central mass concentration also affects the dynamics of gas inflow, guiding it toward a narrow region known as the central molecular zone, a ring of dense gas and dust located just a few hundred light-years from the core. The bulge acts as both reservoir and conduit, collecting material from the disk and directing it inward. It is through this slow movement that the galaxy continues to evolve at its center. Embedded within the bulge are clusters and stellar streams that trace its formation history. Some may be remnants of early mergers, others the products of in situ formation, when the galaxy's central gas clouds were still abundant. The combination of high stellar density and rapid rotation stabilizes the bulge, preventing large-scale disruptions even during interactions with satellite galaxies. Over billions of years, gravitational resonances between the bar and the surrounding disk have redistributed angular momentum, thickening the bulge and giving it its present shape. The result is a structure that appears static but is in fact the long-term outcome of internal motion. The bulge also houses a variety of variable stars such as RR Lyrae and Cepheids, which serve as distance indicators. By mapping their distribution, astronomers have reconstructed the three-dimensional structure of the bulge and determined its size and orientation. The presence of RR Lyrae stars, which are ancient, confirms that the bulge formed early in the Milky Way's history. Meanwhile, younger Cepheids near the plane indicate ongoing star formation, though at a modest level. This coexistence of old and young populations demonstrates that the bulge has never been completely dormant. The environment here is energetic yet orderly, filled with radiation, stellar winds, and faint traces of gas illuminated by starlight. The gravitational potential of the bulge shapes the orbits of the Milky Way's inner globular clusters, many of which swing close to the center before returning to distant apogees in the halo. These interactions gradually strip material from the clusters, adding more stars to the bulge's diffuse light. At the same time, the bulge's dense core shields the galaxy's center from external perturbations, preserving its stability. When viewed in infrared wavelengths, the Milky Way's bulge glows as a smooth golden ellipse surrounded by the darker outlines of dust lanes that curve into the bar. The scene conveys a sense of balance, the outward pull of rotation matched by the inward grip of gravity, the constant motion of countless stars producing the illusion of stillness. The bulge represents the transition from the broad patterned disk to the compact core. It marks the point where the galaxy's history becomes concentrated, where the quiet of ancient stars merges with the slow churn of gas feeding the center. Moving inward from here, the stars become more densely packed, the light more intense, and the influence of the central gravitational source. The supermassive black hole begins to dominate the dynamics of the region. Deep inside the Milky Way's central regions lies the dense and complex environment known as the central molecular zone, a broad ring of gas and dust that encircles the very core of the galaxy. It spans roughly 1,000 light-years in diameter and holds some of the most extreme conditions found anywhere within the Milky Way. Here the interstellar medium is compressed into thick clouds, heated by radiation, stirred by turbulence, and sculpted by gravity into tangled filaments and dense knots. Despite the high energy surrounding it, this region maintains a steady balance between chaos and order, its motions governed by the gravitational pull of the entire bulge and the invisible mass at its center. The central molecular zone contains tens of millions of solar masses of gas, much of it in molecular form, making it one of the richest reservoirs of star-forming material in the galaxy. Yet star formation here proceeds with surprising restraint. The gas is hot, often exceeding 100 degrees above absolute zero, and under immense pressure conditions that seem both to encourage and inhibit collapse. Magnetic fields and turbulence counter gravity, delaying the birth of stars even in places where the gas is dense enough to ignite. When stars do form, they often appear in massive clusters, hundreds or thousands of members born nearly simultaneously from single clouds. These clusters, like the arches and quintuplet clusters, shine brightly in infrared light, illuminating the surrounding dust. Their short-lived high-mass stars contribute strong winds and radiation that shape the surrounding medium, carving out cavities that fill with hot plasma. The interplay between compression and expansion sustains a constant circulation of matter, a cycle that both feeds and restrains the central regions. The central molecular zone is also the site of large-scale inflows of gas from the galactic bar. As the bar rotates, its gravitational influence channels material inward along narrow streams. These inflows spiral toward the center, colliding where their paths intersect, and creating shocks that compress gas into dense ridges. The result is a network of arcs and loops that weave through the inner few hundred light-years, connecting outer regions to the galactic core. Observations in radio wavelengths reveal these structures clearly, showing filaments that rise far above the plane before curving back down, shaped by both gravity and magnetic tension. Some filaments emit non-thermal radiation, evidence that charged particles are being accelerated by magnetic fields and energetic events. The strength of the magnetic field in this region is hundreds of times greater than that in the solar neighborhood, contributing to the stability of the clouds against collapse. Despite the intense activity, the overall appearance of the central molecular zone is one of subdued motion. The orbits of gas and stars are rapid, hundreds of kilometers per second, but the scale is so large that these flows appear steady over human timescales. The region completes one full rotation around the galactic center, roughly every 10 million years. Embedded within it are vast molecular complexes such as ZB2, one of the largest star-forming clouds in the Milky Way. This colossal structure contains more than 1 million solar masses of gas and harbours hundreds of compact cores where new stars are forming. The cloud's dense interior remains invisible in visible light, but glows brightly in millimetre and sub-millimetre wavelengths. Within it, complex organic molecules have been detected, demonstrating that even in these energetic environments, chemistry proceeds toward increasing complexity. The central molecular zone also emits strong infrared radiation due to the heat from embedded stars and the friction of colliding gas streams. Observations show that this region accounts for a significant fraction of the galaxy's total infrared luminosity, even though it occupies only a tiny portion of its volume. The balance between heating and cooling here is delicate too. Much compression would trigger runaway star formation, while too little would allow gas to disperse. Over billions of years, the Milky Way has maintained this equilibrium, ensuring that its central regions remain dynamic but not explosive. Surrounding the dense gas are numerous radio and X-ray structures that trace past energetic events. Arches of high-energy plasma, known as the galactic center radio arcs, extend for hundreds of light-years above and below the plane, marking the paths of magnetic field lines illuminated by relativistic electrons. These features reveal that the core of the Milky Way has experienced periodic outbursts, perhaps linked to activity around its central black hole. Even so, the present epoch is relatively calm. The molecular zone's dense gas moves in stable orbits, and the overall system shows no sign of violent disruption. The interplay of radiation, turbulence, and gravity sustains a gentle rhythm of creation and destruction. Clouds form fragment and dissolve recycling material that will eventually form new generations of stars. This constant turnover feeds the bulge with fresh light and energy, while also delivering matter toward the very center, where the gravitational field steepens dramatically. Temperatures rise, radiation intensifies, and orbits tighten as the influence of the core increases. At distances of only a few dozen light-years from the center, stars and gas move at extraordinary speeds, their paths curved sharply by the pull of an unseen mass. This innermost region is the transition to the galactic nucleus, dominated by the supermassive black hole Sagittarius A star. Yet even here calm prevails on the larger scales. The dense molecular clouds continue to orbit smoothly, forming a rotating ring known as the circumnuclear disk. This ring lies just outside the black hole's immediate sphere of influence, marking the boundary between the central molecular zone and the galactic nucleus. Gas flows through it, slowly spiraling inward toward the event horizon, while magnetic fields guide and regulate its movement. The environment around this region is extreme by terrestrial standards: intense radiation, high temperatures, and strong gravitational gradients. But across the span of light years, the motions remain measured, stable, and predictable. From afar, the central molecular zone would appear as a glowing oval of infrared light surrounding a bright central point embedded in the golden haze of the bulge. It is both the heart and the lungs of the Milky Way, drawing in matter from the disk and releasing energy through the slow pulse of star formation. Every cycle within it, from the drift of gas clouds to the rotation of massive clusters, unfolds over millions of years, contributing to the quiet endurance of the galaxy. As the perspective moves closer still past the rotating molecular ring and into the nucleus itself, the gravitational influence of Sagittarius A star dominates, shaping the motions of everything within a few light years. There, the calm of the molecular zone gives way to the silent intensity of the galactic core. At the very center of the Milky Way lies the galactic nucleus, an environment unlike any other in the galaxy, where the influence of gravity dominates all motion. Here resides Sagittarius, a star, the Milky Way's supermassive black hole, a compact object containing roughly 4 million times the mass of the Sun, confined within a region smaller than the orbit of Mercury. Despite its immense gravity, the area around it is not a place of violent chaos, but of quiet precision, where stars and gas clouds move in tightly ordered orbits governed by an invisible center. The black hole itself cannot be seen directly. Its presence is inferred from the motion of nearby stars, some of which complete full orbits in as little as 16 years. These orbits, mapped with remarkable accuracy, form perfect ellipses that converge on a single dark point. The precision of their paths provides one of the clearest proofs of the black hole's existence. Around this region lies a cluster of young massive stars collectively known as the S stars, their blue light piercing through the surrounding dust when observed in infrared. How such stars formed in an environment dominated by extreme tidal forces remains an open question, but their presence shows that even near a supermassive black hole, conditions can still give rise to new stellar systems. The gravitational field here is steep at a distance of 1 light-year from Sagittarius. Star objects move at hundreds of kilometers per second. Closer in space itself is curved by gravity, bending the paths of photons that graze the event horizon. This invisible boundary marks the limit beyond which not even light can escape, yet the region immediately around it glows faintly in radio and infrared light from infalling gas. This glow, produced by matter heating to millions of degrees before crossing the event horizon, forms the black hole's accretion flow. The flow is irregular and faint, indicating that Sagittarius A star is currently in a quiet phase. In the distant past, it may have been more active, accreting larger amounts of gas and shining as a brilliant source in X-rays and ultraviolet light. Today, it radiates only modestly, releasing energy, equivalent to that of a single bright star, though from a volume only a few times larger than the Sun itself. The accretion process is gentle filaments of gas drift inward from the surrounding molecular ring, spiraling slowly through magnetic channels before vanishing. The infell is intermittent, punctuated by brief flares when material suddenly heats and emits bursts of radiation. These flares last for only minutes or hours, but are strong enough to illuminate nearby clouds, producing delayed reflections that echo across light years. Such reflections, seen as faint X-ray glows, reveal that the black hole's activity fluctuates over time, surrounding Sagittarius. A star is a cluster of old stars known as the nuclear star cluster, one of the densest stellar regions in the Milky Way. Within just a few light years of the center, millions of stars crowd together, their combined mass exceeding that of the black hole itself. The density here is extraordinary. If the same concentration existed near the Sun, the night sky would be ablaze with thousands of bright points. Yet despite this crowding, the system remains dynamically stable. Each star follows its own orbit, moving in a gravitational ballet that has persisted for billions of years. Collisions are rare because the stars move so swiftly, passing one another at high speeds without physical contact. The gravitational field of the black hole acts as a stabilizing anchor, keeping the cluster bound and orderly. Around the cluster, streams of gas orbit in rings and arcs, forming structures known as mini-spirals. These filaments trace the flow of material inward and are illuminated by ultraviolet radiation from nearby young stars. They provide the final link between the central molecular zone and the black hole's accretion flow, carrying matter inward at a measured pace. At distances of only a few tenths of a light-year, the gas begins to glow in infrared and X-rays heated by compression and friction. Some of it is captured. The rest escapes outward, feeding faint winds that rise perpendicular to the galactic plane. These winds may connect to larger structures seen thousands of light-years away, giant lobes of radio emission, called the Fermi bubbles, remnants of ancient outbursts from the galactic nucleus. Though immense, these features formed long ago. Today the nucleus is tranquil, its motions governed by slow cycles rather than eruptions. The silence of Sagittarius, a star, belies its power. Every star and cloud within the inner few hundred light-years responds to its gravity, moving in resonance with the bar and bulge beyond. The energy released by even small amounts of infalling gas is enough to influence the surrounding region, heating the ambient plasma and sustaining the delicate balance that defines the Milky Way's core. From the outer disk to this central point, gravity binds all layers of the galaxy into a coherent system, each region influencing the next in a continuous chain of motion. The study of the galactic center has provided deep insight into how galaxies evolve. Many external galaxies show similar structures, dense cores with central black holes, whose masses correlate with the size of their bulges. This connection suggests that the growth of black holes and galaxies is intertwined, each regulating the other through feedback mechanisms over cosmic time. In the Milky Way, this relationship appears calm and mature, reflecting a long period of equilibrium. The stars of the nuclear cluster orbit in silence, the black hole accretes sparingly, and the surrounding gas flows with steady rhythm. Occasionally, small bodies, comets, asteroids, or even stray stars may wander too close, torn apart by tidal forces and consumed. Yet such events are rare, and most of the time the center remains dark and still. Seen from a distance, the galactic nucleus would not appear as a violent beacon, but as a subdued point of light surrounded by the golden radiance of the bulge and the soft spiral of the disk beyond. The gravitational influence of Sagittarius, a star, reaches outward, invisibly linking every star in the Milky Way to its motion. It acts as the hidden anchor of the entire system, ensuring that the galaxy's rotation and structure remain in balance. In the vast timescales of cosmic history, even this calm center will change. Gas will flow inward, activity will rise and fall, but for now the Milky Way rests in equilibrium, a quiet spiral encircling a silent core. Within this stillness, gravity, radiation, and time maintain their endless conversation, shaping the galaxy's form without ever disturbing its calm. From the edge of the halo to the black hole's unseen boundary, the Milky Way endures as a single, luminous organism, breathing through cycles of creation and rest, bound together by the invisible force that holds all things in place.